For a brief moment, it seemed that the story of 3I Atlas was finally settling into place. The object had already passed its closest approach to the Sun, and according to familiar models, its activity should have begun to fade. Then new observations arrived, made at a moment of near-solar opposition, when Atlas could be seen from Earth under an ideal viewing geometry. What astronomers found was not a subtle refinement of earlier data. Distinct and unexpected structures began to emerge in the surrounding dust and in the shape of the tail. Even more surprising was the object's behavior after perihelion. Instead of weakening, its activity appeared to intensify. The data pointed toward a delayed activation, stronger than most predictions had anticipated. Which brings us to a question that cannot be ignored. What exactly happened to 3I Atlas after the last update? And why are we only beginning to see its implications now? In the life of a typical comet, perihelion marks a clear turning point. As the object approaches the Sun, increasing heat drives the sublimation of surface ices, gradually building up activity. At perihelion, this process usually reaches its maximum. After that, as solar energy decreases with distance, activity is expected to fade in a predictable way. This pattern has shaped how cometary evolution has been modeled for decades. 3I Atlas does not follow this sequence. Instead of peaking near perihelion, its most intense activity appears to begin after the closest approach to the Sun. The timing alone is enough to raise concern, because it reverses the expected cause and effect. Heat arrives first, yet the strongest response comes later. This behavior undermines predictions that assumed surface-driven sublimation as the dominant process. Models calibrated to decades of solar system comets begin to lose their explanatory power, and that leaves us facing a fundamental problem rather than a minor anomaly. Why would an object respond most strongly only after passing through the region of maximum solar heating? What physical process could reverse a sequence we thought we understood so well? When astronomers began analyzing post-perihelion data, one signal stood out almost immediately. Observations from SphereX showed that Atlas was not merely active, it was unusually bright. Both dust and gas emissions intensified far beyond what existing predictions had allowed for. This level of brightening is rarely seen in comets native to our own solar system. Even large, well-studied comets tend to show a more restrained response at this stage. At first glance, one might assume this is simply sunlight reflecting off newly released material. But the data does not fully support that explanation. The brightness increase appears too strong and too structured to be explained by surface ice sublimation alone. Instead, the observations hint at a more complex source of material and energy. Something beyond a passive response to solar heating seems to be involved. It is at moments like this that careful observation becomes essential, because this is where small anomalies begin to reshape much larger assumptions, and it leads us to another question that cannot be ignored. Is this energy coming from the environment around Atlas, or from processes taking place within the object itself? If what we are seeing from 3I Atlas feels unlike anything you would expect from a normal comet, then this story is far from over. Consider subscribing and continue with us as we try to make sense of what the data is really telling us. As the data continued to accumulate, another inconsistency began to stand out. Spectral observations from multiple telescopes revealed that Atlas was changing color over time. On its own, a change in color would not be unusual. As objects heat up, their emission typically shifts in a predictable direction. Warmer conditions generally lead to a gradual reddening of the observed light. Atlas does not follow this progression. Instead of a smooth transition toward redder wavelengths, its spectrum shows a more complex pattern. At different times, different colors become more pronounced. This suggests that the dust and gas surrounding Atlas are not uniform in composition or behavior. Each color corresponds to a specific physical process or molecular signature. Green, blue, and red emissions are not interchangeable. They point to different materials, different energies, and possibly different sources. Taken together, the spectral data suggests that Atlas is not responding as a single, simple system. Instead, multiple processes may be unfolding at once, some of them in unexpected order. It is this mismatch that makes the spectral data increasingly difficult to interpret. So what could force an emission spectrum to move against physical trends we once considered well established? To understand what the changing colors might mean, scientists turn to the chemistry behind the light. Spectral data collected before and after perihelion revealed a complex mixture of gases surrounding Atlas: carbon dioxide, cyanogen, water vapor, and a range of organic compounds appeared with notable strength. None of these substances are unusual on their own. They have all been detected in comets before. What is unusual is their relative balance. In most solar system comets, water ice dominates the picture, both chemically and energetically. Other gases tend to play secondary roles, emerging as temperature rises. Atlas does not fit comfortably into that pattern. Some of the detected gases appear more prominent than water would suggest. This hints that the volatile inventory of Atlas may have formed under different conditions that do not closely resemble the environment in which most solar system comets originated. Temperature, pressure, and radiation history all shape chemical composition. A shift in chemistry implies a shift in origin. Are the measurements we are seeing reflecting an environment of formation around another star? As the chemical picture grew more complex, another anomaly began to emerge in Atlas's motion. Before perihelion, the object followed a trajectory that closely matched gravitational predictions. Its path could be explained almost entirely by the gravitational influence of the Sun and planets. After perihelion, that simplicity disappeared. A clear non-gravitational acceleration began to appear in the tracking data. The magnitude of this acceleration was not trivial. It was strong enough to shift predicted positions by hundreds of kilometers per day. Effects of this scale cannot be dismissed as measurement noise. What makes this even more puzzling is the timing. The acceleration did not peak near perihelion, when surface heating and outgassing should be strongest. Instead, it emerged only after Atlas had already passed through the region of maximum solar energy. This behavior does not align with classical outgassing models used for comets. In those models, non-gravitational forces are tightly coupled to surface sublimation. Atlas appears to decouple these processes in time. Such a delay points toward an internal mechanism rather than a purely surface-driven one, a process that activates only after thermal energy has already been absorbed and redistributed. So why does the push appear only after the hottest part of the journey is already behind it? Once the non-gravitational acceleration was accounted for, the shape of Atlas's trajectory began to tell a clearer story. The object's actual path no longer aligned with a purely gravitational solution. This deviation was not random. It showed a consistent direction over time. Random measurement noise would scatter residuals in all directions. That is not what the data shows. Nor does the pattern resemble chaotic thrusts from irregular, short-lived gas release. In those cases, The resulting motion would fluctuate erratically. Atlas, instead, exhibits a deviation that is smooth and coherent. Such behavior implies the presence of a sustained force, a force that persists long enough to shape the trajectory in a measurable way. This is where many existing models begin to struggle. They can reproduce brief anomalies, but not an orderly, directional push sustained over time. At this stage, the data is no longer merely surprising. It actively resists simple explanations. So how ordered do you think a force can be? If it arises from a natural object, as attention shifted from the trajectory to the source of the force, the images revealed something even more unusual. At least 7 distinct jets could be identified, emerging from Atlas. Each jet remained sharply defined, rather than blending into a diffuse cloud. Even more striking was their stability over time. The jets maintained nearly the same geometry for hours at a time. This persistence is difficult to reconcile with Atlas's rotation. Estimates suggest a rotation period of roughly 16 hours. Under Zook, rotation, surface jets would normally be smeared into curved or spiral structures. That is what is commonly observed in active comets. Atlas does not behave that way. Several jets appear to preserve their orientation, some even pointing broadly toward the Sun. This kind of directional stability is extremely rare in cometary observations. It suggests that the jets are not simply surface features being dragged around by rotation. Instead, they may be anchored by deeper or more structured regions within the object. So what kind of structure could preserve such geometry on a rapidly rotating body? If you genuinely care about 3I Atlas and want to understand what makes it so unusual, consider subscribing. And continue with us as we follow the data and explore what is truly shaping this object. Not long after the stable jets were identified, Atlas underwent another dramatic transformation. Within a span of roughly 24 hours, the morphology of its tail changed significantly. A new structure rapidly extended outward from the nucleus. The tail reached a length of nearly 3 million kilometers, on astronomical scales. This is an enormous structure to form in such a short time. Its appearance was also unusual. Rather than resembling a classic ion tail, it appeared diffuse and smoke-like. This texture suggests material spreading en masse rather than being gently sculpted by the solar wind. What makes this especially puzzling is the energy balance. Measurements of surface heating do not easily account for such a rapid and extensive release. Gradual sublimation would struggle to produce this scale of change. The observations instead point toward a more sudden and forceful event, one that may involve material being expelled from deeper within the object. This was not a slow, fading, or gentle evolution. It was a rapid reconfiguration of structure on a planetary scale. It becomes difficult to imagine what kind of mechanism could produce a structure this large, this quickly. Among the many unexpected features observed around Atlas, one stands out for defying basic intuition. Early in the observations, an anti-tail began to appear. At first, it seemed transient, fading from view as conditions changed. But later, as Atlas moved closer to the Sun, the anti-tail returned. This alone would be unusual. What makes it more puzzling is the environment in which it persisted. Near the Sun, the solar wind is at its strongest. Radiation pressure and charged particles should sweep material firmly away from the Sun. Under such conditions, an anti-tail should not survive. Standard physical models offer little support for its presence. Yet the observational data leaves little room for doubt. The anti-tail is clearly resolved, repeatedly imaged, and consistently oriented. This is not a projection effect or a fleeting artifact. It represents material behaving in a way that challenges the expected flow of energy. At this point, direction becomes as important as scale. How can material move against the dominant flow of solar energy? By this stage of its journey, Atlas was operating under extreme conditions. Large amounts of gas and dust were being lost into space. The object was exposed to intense solar heating. Surrounding plasma and radiation added further stress to its structure. For many comets, this combination is catastrophic. Fragmentation, splitting, or complete disintegration are common outcomes. Atlas did not follow that pattern. Despite sustained mass loss and extreme external forces, it remained intact. No clear signs of structural collapse were observed. This resilience is difficult to reconcile with a loosely bound, porous nucleus. Instead, it suggests a body that is denser and mechanically stronger than expected. Possibly a nucleus held together by more than fragile ice and dust. At this point, survival itself becomes a piece of data, and it forces a deeper question about its internal makeup. What, then, is the true internal structure of Atlas? As questions about Atlas's strength grew, attention naturally turned to its size. Initial estimates placed the object at only a few kilometers across. These conservative values were based on limited brightness data and standard assumptions about reflectivity. As more observations accumulated, alternative estimates began to emerge. Some analyses suggest a diameter approaching 10 kilometers. If correct, this would make Atlas significantly larger than previously observed interstellar visitors. Both Oumuamua and Borisov appear smaller by comparison. Objects of this scale are extremely rare among known interstellar detections. Size matters not only for physical strength, but also for statistics. A single large detection can dramatically reshape estimates of how many such objects exist in the galaxy. It suggests that interstellar space may host more massive bodies than we previously assumed. And that possibility carries consequences far beyond this one object. At this point, size becomes a clue, not just a measurement. Where could an object this large have formed before being cast into interstellar space? Once size enters the discussion, probability inevitably follows. For an object like Atlas to exist at all, several unlikely conditions must align. It would have wandered through interstellar space for billions of years. During that time, it would need to avoid destructive collisions. It would also have to resist gradual erosion from radiation and dust. Eventually, it would need to pass close enough to a star to become detectable. In this case, that star happened to be the Sun. Even that is not enough. This passage had to occur at a moment when our instruments were capable of seeing it. Not millions of years earlier. Not millions of years later. Taken individually. Each condition is improbable. Taken together, they begin to feel almost implausible. And yet, Atlas is here, moving through the inner solar system, visible to our telescopes. This forces an uncomfortable reassessment. Is this an extraordinary stroke of luck? Or does it suggest that our estimates of interstellar populations are fundamentally incomplete? Are we underestimating how many objects like Atlas truly roam the galaxy? To place Atlas in context, it helps to look back at the first interstellar visitor we ever identified. Oumuamua remains one of the most puzzling objects ever observed passing through the solar system. Unlike Atlas, it showed no visible coma. There were no obvious jets or extended clouds of gas and dust. And yet, its motion revealed a measurable non-gravitational acceleration. This acceleration appeared without any clear signs of outgassing. The object's shape was also unusual. inferred to be highly elongated or flattened. Its thermal response did not resemble that of a typical comet, nor did its inferred composition align with familiar icy bodies. Atlas presents a very different picture. It displays a coma, Restraint, jets, and strong post-perihelion activity. Its chemistry, morphology, and dynamics follow a separate pattern. Taken together, these differences suggest that the two objects are not closely related. They may share an interstellar origin, but little else. This comparison complicates how we think about interstellar objects as a category. The label may be hiding a wide diversity rather than describing a single class. Is interstellar object simply too broad a term to capture what we are seeing? After comparing Atlas with Oumuamua, a second reference point becomes unavoidable. That object is Borisov, the first, clearly comet-like interstellar visitor ever observed. Unlike Oumuamua, Borisov displayed a classic coma and tail. Its activity followed a pattern broadly consistent with solar system comets. In that sense, Borisov felt familiar. Atlas does not. Even at comparable distance, Atlas shows much stronger activity. Its gas and dust output exceed what was measured from Borisov. The non-gravitational acceleration acting on Atlas is also significantly larger. Borisov exhibited only modest deviations from gravitational motion. Atlas, by contrast, shows sustained and structured forces. Borisov showed no prominent anti-tail, nor did it display a stable system of persistent jets. In many ways, Borisov fits the textbook definition of an interstellar comet. Atlas breaks that definition repeatedly. This comparison reverses an intuitive assumption. Perhaps Atlas is not the outlier after all, and perhaps Borisov is the simpler case. Could it be that Borisov, not Atlas, represents the exception? After comparisons with known interstellar visitors, the question of origin becomes unavoidable. The answer begins with its trajectory. Atlas follows a hyperbolic path through the solar system. Such a trajectory indicates that the object is not gravitationally bound to the Sun. It is a visitor, not a resident. This alone confirms an origin beyond our planetary neighborhood. But knowing that Atlas came from elsewhere does not tell us where exactly that was. Its incoming path cannot be traced back to a specific star or system. Over billions of years, gravitational encounters erase that information. What remains are only broad possibilities. Atlas may have formed in the distant outskirts of a planetary disk, or it may originate from a far more extreme environment altogether, one with different temperatures, pressures, and chemical histories. Without a way to retrace its path, certainty remains out of reach. Origin, in this case, becomes a matter of inference rather than proof. Which brings us to a more fundamental question. What kind of environment could produce an object like Atlas when direct knowledge of origin is lost? Chemistry becomes one of the few remaining guides. The gases released by Atlas do not form a random mixture. Carbon dioxide appears to play a dominant role. This alone is noteworthy. In most solar system comets, water is the primary volatile driving activity. Carbon dioxide is usually secondary, becoming important only under specific conditions. Atlas shows a different balance. The relative proportions of gases do not closely resemble those seen in inner solar system comets. Such differences point toward formation in a colder environment. Temperature controls which volatiles are trapped, preserved, or lost during formation. Pressure plays an equally important role. It influences how ices condense and how porous a body becomes. Together, temperature and pressure leave a lasting imprint on chemistry over time. Thermal history adds another layer of complexity. Heating events can alter composition without erasing it entirely. What we observe today may be a modified record, not a pristine one. Even so, the chemistry still reflects conditions that differ from our own neighborhood, not just a different object, but a different history. Which brings us back to a question that chemistry quietly raises. Could this composition be reflecting the environment of a different stellar system? As the implications of Atlas began to widen, the flow of new information noticeably slowed. This delay was not accidental. Complex observations require careful cross-verification. Spectral data, in particular, takes time to analyze and interpret. Signals must be separated from noise, and instruments from different teams must agree. In cases like this, caution becomes a scientific necessity. Rushed conclusions risk collapsing under later scrutiny. So, researchers slow down, double-check, and wait. But this necessary patience creates an unintended consequence. Gaps begin to form between what is observed and what is publicly confirmed. In those gaps, questions naturally grow. And where questions accumulate, imagination often follows, not because the data invites speculation, but because silence always does. At this stage, absence of information becomes part of the story, and it leads to a simple but persistent uncertainty. How much remains unseen, unanalyzed, or simply not yet shared? At this point, the difficulty is no longer a lack of data alone. It is that no single model can account for everything that has been observed. Different hypotheses succeed in explaining different aspects of Atlas. One may fit the chemistry. Another may describe the dynamics. A third might address the morphology of jets and tails. But none of them bring all the pieces together. There is no unified explanation that holds across every dataset. This places the phenomenon in a rare scientific state, a state where models remain open rather than closed. In such moments, science becomes deliberately cautious. Claims are restrained, and uncertainty is openly acknowledged. Yet caution does not imply disinterest. In fact, this is often when curiosity is at its strongest, because unresolved phenomena carry the potential to reshape understanding, not by force, but by persistence. When does an observation become significant enough to force a revision of our models? At moments like this, science naturally approaches a boundary it has encountered many times before. Not a boundary between truth and error, but between what is firmly known and what is only partially constrained. On one side lies data measurements, spectra, trajectories, uncertainties carefully quantified. On the other lies imagination, the human impulse to fill gaps, connect patterns, and ask what might exist beyond current evidence. Science cannot progress without imagination, because every hypothesis begins as an act of creative inference. But imagination on its own is not enough. Without discipline, it drifts into speculation, and speculation can quickly outrun reality. That is why evidence matters. Not to suppress imagination, but to anchor it to the physical world. The history of science is shaped by this balance. Too little imagination, and progress stalls. Too much, and meaning dissolves. The breakthroughs that endure are those that hold both in tension, beginning with strange questions and surviving only when data eventually catches up. Atlas now sits directly on that boundary. Its behavior can easily collapse into familiar models. Yet it does not break them outright. It does not demand an immediate rewrite of physics, but it quietly challenges assumptions about cometary behavior, about how interstellar objects form, and about how diverse planetary systems may be across the galaxy. In situations like this, restraint becomes as important as curiosity. Science must move forward carefully, observing more, measuring better, and allowing patterns to emerge rather than forcing them into premature narratives. But restraint does not mean silence, and it does not mean avoiding difficult questions. Questions are how science decides where to look next, what to measure, and which missions to design. Atlas forces that balance into view, open but not reckless, curious but not credulous, willing to imagine but unwilling to abandon evidence. It is not just an unusual object passing through the solar system, but a reminder of how scientific understanding actually advances, step by step, through uncertainty rather than certainty. How far should imagination be allowed to go? When an object resists natural explanation, an obvious question sometimes surfaces, and then just as quickly recedes. Not because it is forbidden, but because science operates under strict rules of evidence. A technological hypothesis requires direct, unambiguous signatures, signals that cannot be replicated by natural processes, structures that demand intentional design rather than emergent physics. In the case of Atlas, such evidence does not exist. What we have are anomalies, not diagnostics, patterns that are difficult to explain, but not patterns that uniquely point to technology. Without that threshold being crossed, science does what it is designed to do. It withholds judgment. There are also practical reasons for caution. History shows that premature technological claims carry heavy communicative risk. They can overshadow careful analysis, polarize discourse, and erode public trust when later revisions become necessary. For this reason, science systematically prioritizes natural explanations, not because they are always correct, but because they are testable, falsifiable, and historically productive. Importantly, prioritization is not exclusion. Hypotheses are not banned, they are deferred, placed on hold until evidence demands reconsideration. Atlas sits uncomfortably close to that boundary, not forcing a technological explanation, but reminding us why science moves slowly near it. Is there any hypothesis that should never be allowed to be asked? If technological explanations are set aside, the remaining possibilities still leave much to consider. One option is that Atlas possesses an unusually dense core, not a loosely bound mixture of ice and dust, but something mechanically stronger. A nucleus enriched with metals or refractory materials could behave very differently under stress. Such a composition would help explain both its resilience and its ordered outgassing. Structure matters as much as composition. A compact internal architecture could channel energy and material in ways current models do not capture. There is also the possibility of physical reactions we have not yet fully modeled. Phase changes, delayed thermal diffusion, or pressure-driven fractures could all play a role. These processes may be rare, but not impossible. Atlas may simply sit at an extreme end of natural variation, an object formed from uncommon materials, under uncommon conditions, with an uncommon thermal history. If so, it does not break physics. It exposes where our descriptions are incomplete. Cometary physics has always evolved with new observations. Atlas may be pointing toward chapters that have not yet been written. What, then, is missing from our current understanding of cometary physics? For all its mysteries, Atlas offers something rare in astronomy proximity. For a brief period, it passed closer to Earth than any known interstellar object before it. That distance matters. It determines how much detail can be resolved, how faint structures can be separated from noise, and how confidently models can be tested. During this window, both ground-based observatories and space telescopes were able to observe Atlas at unprecedented resolution. Features that would normally blur into uncertainty became measurable. Jets could be tracked. Spectral lines separated, and subtle changes followed over time. Opportunities like this do not repeat easily. Interstellar objects do not linger. Their paths are fleeting, their trajectories unbound. Once Atlas moves on, the geometry degrades, signals weaken, and the chance for high-fidelity observation fades with it. There will be other interstellar visitors in the future, but none with the same timing, distance, or combination of properties. In that sense, this is a once-in-a-lifetime dataset, a narrow observational window that is already beginning to close. What remains is the question of sufficiency. Will this brief moment of clarity provide enough information to settle the open questions? Or will Atlas leave behind answers that remain just out of reach? Is this dataset enough to reach closure? For all the data we have gathered, there are limits that no amount of observation can overcome. Atlas is already on its way out of the solar system, and there is no realistic way to follow it. No spacecraft was positioned to intercept it. No probe will sample its material. No mission will circle back for a second look. Once it leaves, it is gone for good. What remains is information at a distance, light captured by instruments, spectra interpreted through models, motions inferred from points of data, all of it valuable, but all of it indirect. There will be no way to test certain ideas conclusively, no way to measure internal structure directly, no way to confirm composition beyond what remote sensing allows. Some questions will simply remain unanswered. This is a familiar reality in astronomy. Much of what we study cannot be touched, revisited, or corrected later. Opportunities appear briefly, then close forever. Atlas is one of those cases. A chapter observed in passing, never to be reopened. What we know will always be partial. What we infer will always carry uncertainty. And yet, this incomplete record is all that remains. So the question is not what we will discover next. It is what will remain forever unknown. In the end, Atlas does not confront science with a single unanswered question, but with a posture it must adopt. Not everything yields a rapid explanation. Not every anomaly resolves itself within existing frameworks. Sometimes data arrives before theory is ready to receive it. When that happens, uncertainty is not a failure of science, but a feature of it. Science is often imagined as a steady march towards certainty. In reality, it moves unevenly. Periods of clarity are followed by stretches of confusion. Observations accumulate faster than understanding. Models lag behind reality. Atlas is one of those moments where the gap becomes visible, where the honest response is not confidence, but restraint. This does not diminish science. It strengthens it, because acknowledging uncertainty preserves credibility. It prevents premature conclusions from hardening into dogma. Atlas reminds us that understanding is provisional, always subject to revision. and that patience is not the absence of progress, but its precondition. In this sense, Atlas is less a mystery to be solved than a lesson to be absorbed. It does not demand answers. It demands honesty about what we do not yet know, and discipline in how we respond to that absence. Atlas will leave the solar system the same way it arrived. It will not wait for our models or our conclusions. What remains is a brief record of light, motion, and matter, captured in passing. Some of it we understand. Some of it we may never fully resolve. That is not a failure of science. It is a reminder of its limits. If 3I Atlas has held your attention, then this story is not really about one object. It is about how carefully we choose to think when answers are incomplete. If you care about following that process, consider subscribing and continue this journey with us.